Hello, everyone. So welcome to this section. I'm going to talk about mathematical proofs, which is essential for your study, in your further math. Okay. So in this section, I will use very basic examples and definitions and proving. Okay. So these are not going to be the statements are not going to be difficult. But it serves as the purpose to tell you how to prove things in your future classes. Okay. So first of all, you always see in your classes there is definition. So definition will let me introduce two definitions which are very easy. Okay. So let's C be an integer. So C is odd if there is or there exists integer k such that, so you have a c equals 2k plus 1. Okay, so c is even if there exists an integer, probably also k, such that c equals 2k. So there are a few things that should be noticed in definitions. Okay, so first of all, there are some words to be defined. So there are some words which are originally you don't know the definition. Okay, you don't know what it means. So then you look at the definition and you know what it means. Okay, so the word is usually highlighted or underscored, and it's important to underscore it since it's the only word that is unknown in your sentence. And if you don't do it, then yeah, it will cause many trouble. Okay. Here, the if is meaning that we call C to be odd if the following thing happens. Okay. So this if is not an implication. It's not this happened, then C is odd. It's not an implication, but rather this is a defining thing. So if you check on dictionary, you know that if you check a word, then it shows a definition, right? This is the exact same thing. So if you check this word odd, then it will show you the definition as follows. So that's why you need to underscore it and understand that it's not an implication. Okay. So you know what is odd, what is even. So some will write we say, to emphasize that is a definition. Some will write is said to be. Usually you only choose one. Okay. Some will will use there is instead of there exists, but it means the same thing. But all of these are just stylish choice. So it need not to be any of these. Okay. So even if you just write this, it's still correct. Okay. So a few more notations for your future studies. So here is the for any or for all. So it depends on the context. I don't understand what the difference it is, but it means all of them have the same property. Okay, this is a there exists or there is. I mean, if you write as there exists, then you can do this or there are. Okay, so it's for some elements that that's true. It's not necessarily for all that's true. Okay, so you have this is such that. There are other notations, but these are the most common ones. Okay, you still have this. So this is in. So for example, 2 is in the set of integers, but you usually read as follows. So 2 is an integer, although it really means 2 is in the set of the integers. Okay, So this is in. Okay, all right. So we are going to like discuss about discuss how to prove things, right? So the first thing is like to show you direct proofs. So like a question, or like you can write to proof in your like answer. Okay, question. I will use the question, and then I will show you the true proof. Okay, if A and B, sorry, A and B are odd numbers, then AB is odd. Okay. So we defined about the like defined above that like odd numbers mean like odd integers. Okay, so there's no like decimal things we call it as odd. There may be some like in other definitions, but not in this section. Okay, so if A and B are odd numbers, then AB is odd. So how we prove it? So you always like you can always, I mean, it's not an essential thing, of course. So when you are writing your solution, or as a student, I'm not saying like as a researcher you still do this, okay? But as a student, you always begin your thing with like the thing that you are going to prove, okay, is odd. So this is something you are proving. So at your last step, it should be like something like this, okay? So this is a direct proof. So usually how we start a direct proof is as follows. So there are some criteria, there are some like assumptions that are imposed in the question. Say like A and B are odd numbers. So we know that, okay? So we write like A is an odd number, A is odd number. It means that there exists K1 such that A equals to K1 plus 1, right? So B is odd, means that there exists K2 such that like B equals to K2 plus 1. So remember, even if the definition only use K, you can use any letter here. And you don't use the same letter, since like A and B can be quite different. So you use like a K or L or K1 or K2 or anything you like, but you don't use the same letter, okay? Now you have this, so these are the definitions. So these are from definition. You don't need to write anything I wrote in blue. It's just showing you like what is the structure of the proof, okay? So now you're proving something about AB. So how to do something about AB? So AB, well, is a multiplication of A and B. So of course you are going to like multiply these two together, right? And then you expand. So I'm going to skip the expanding step, since like it's not like very informative. And now you can like factor out 2, except the 1. Okay, you don't factor out the 1, and then you are factoring the 2 like this. Okay. So since sorry, I should have said this. That's my fault. So it's like in integer. So there exists integer K, right? I hope that I'm not making mistake upstairs. Okay, you can see like here, you have integer K. That's why here you should also like make it into integer. Okay. So now, since K1 and K2 are integers, then 2K1 K2 plus K1 plus K2. So it's the addition and multiplication of integers. It's still an integer, right? So AB is odd by definition. So here is the number that we are seeking to make it to an odd number. Okay. So this is what it means to be odd, and that's why it's a direct proof. So how a direct proof looks like? So there are something from definition and something like from assumptions. So here are from assumptions. and then you try to do some calculation or some steps, and then finally you get your conclusion. It's direct, so you don't like have some like funny things in between. Okay. So let's do another example. This time we are going to focus on proof by contradiction. Okay, I would just say like to prove that yeah, I didn't even say proof that. So let's say, so if AB is odd, then so are A and B. So it means that like if AB is odd, then A is odd and B is odd. Okay. So to prove A is odd and B is odd. So how you like you're going to do it? So it is like you can probably do it like by direct proof, but it could be challenging. So one of the techniques to get through like these kind of questions are by contradiction. Okay. So suppose not. So this is like the common like starting for proof by contradiction. Okay. Suppose not. What it means is like we're supposed the conclusion that we are proving is not true. Okay. Then we're going to show that there are some problems with these kind of assumptions. Right? That's the thing that we are going to show. Okay. Suppose not, then what it means is like either then A is even or B is even. So we are going to negate this sentence. Okay. So what is the opposite of A is odd and B is odd? It's not A is even and B is even. It's not true. But you need to change the and to or. You can see like per by this diagram. So you have odd, even, odd, even. So this is meaning that A is odd and B is odd, meaning that it's in this square. So how to like negate it? The only negation is like this L-shaped thing, and this L-shaped thing is given by like A is even or B is even. So take the union of them. So if you say like A is even and B is even, then it's just this grid, which is not true. It's not a negation of the above statements. Okay. So now you have A is even or B is even. But you can imagine if A is even, we do something like we try to continue our proof, and if we then do the like thing for B is even, it's going to be the same. I'm not saying like the A and B, the letters are the same, but I'm saying the row of A and B, the row of A and B here are the same. Since like in A times B equals B times A, right? So A and B are indistinguishable in this context. So we will say without loss of generality, like suppose A is even. So some writes like this as like WLOG. Okay. It's meaning that like without loss of generality. But what it actually means is that if you have this case, then for other cases, it's similar. It's too similar that we don't bother to write. Okay. So if you have A is even, if you prove a contradiction, and if you have B is even, then you are just doing by symmetry. So you will replace A by B, and you will replace B by A. Okay. Now, suppose A is even, then what it means? So by definition, so you know like by definition, that like A, there exists like a K such that like a pernicious K, A equals to K. Okay. So we have only one assumption. The assumption is AB is odd. So we are going to derive our contradiction with that assumption. So AB is odd, we are going to calculate AB. But only thing we know about A and B is the A equals to K. So let's do it. Right? But this is just 2K times B. And like and you will know that like since KB are integers, then KB is integer, right? So the multiplication of them is still an integer. And that's why AB is even, which is not correct, right? You know that like AB is odd. Now you get AB is even. So it's a contradiction. Here, of course, I assumed that if an integer is not even, if it's even, that is not odd. Okay. So, but like you know that like integers can only be like either even or odd. Then like you know this is correct. So we prove the statements like here purely by like making a contradiction. So we don't know how exactly directly to prove it, but this method gives you a way to show it by contradiction, which is a very like essential part in like a development of mathematics. So many things we don't know how to construct, but we argue by contradiction that something must exist, even though we don't know how to construct. Okay. So some proof like in terms of direct proof, if you prove something is existing, it's called like a constructive proof. It's like it shows you how to construct that thing, even though the construction may be very difficult. But this kind of proof by contradiction is not going to be constructive, since like you can't construct your like thing purely by this kind of contradiction. But you know that is true. Okay. So now we are going to introduce another tool, which is like usually called like it suffices to show. So it's very common. Okay. Question: if A is a real number, then you want to show that like A squared plus 1 is non-negative. So in fact, you know that this is positive, but like let's try to do this. So to make it extremely easy, okay? So to prove that A squared plus 1 is non-negative. And then I'm going to say the following. It suffices to show that A squared is non-negative. Okay. Or even if I change it to positive, it still works. Okay. So let's change it to positive. So now if A squared is non-negative, why I say this sentence? Am I subtracting 1? No, that's not the case. Okay. So why I'm saying this is as follows. If I'm just only saying if we can show that A squared is non-negative, then we know that A squared plus 1, since you are adding 1, it must be positive. Okay. So if we have this is true, then we know that the above is true. It's meant like it suffices to show this wordings is meaning this. So we are going to show this since this implies this. It need not to be IFFF, okay? It need not to be like this implies this, which is false. We only need this to be true. Okay. So it becomes like a squared is non-negative. So when you see like this kind of statements, it means that like your like teacher or like the proof is going to shift its focus, not to prove this, but to prove this. Okay. So like the actual proof is not that exciting. So let's try to like do in a few lines. So the case 1, a is bigger than 0. Then you try to multiply a on both sides. Since a is positive, then it doesn't change the sign. Case 2, a equals 0. Then a squared is 0. Nothing special. A is smaller than 0. Then since a is negative, so when you multiply on both sides, it will change the bigger than sign. Okay, it's bigger than 0. And here finishes the proof. Since we show that a squared is non-negative. Okay. So you can see that like in the whole proof, a squared plus 1 doesn't even show up. Since like we don't need it anymore by this sentence. Okay. So last but not least, we are going to introduce MI, mathematical induction, which is also essential for your study. So let n be an integer, like for a positive integer. So show the n like from 1 square to n square, it sum up to be like this. Okay, it's just some random formula. You can easily try online. And there are many proofs of this, but like we are going to present some cheapest proof, which is called MI. I mean, I'm not saying that like any proof by MI is cheap. Okay, it's just I'm just saying that like there are many ways to understand this formula, but like the easiest way to show that it's true is just by like using MI. So what is the structure of MI? So we are going to show in below 2 things. So there's a thing called base case. So it's usually like you choose a number or 2 numbers. You probably sometimes you need more than 1. Okay, but here you only need 1 number. So when this n equals 1 is true, okay, so this is the base case we're going to show. Inductive step is to show as follows. If n equals k is true, like when n equals k, the statement is true, then n equals k plus 1, the statement is still true. Okay? Statement. Okay? So now, here is the proof. Why? So now for n equals 1 is true. But if you know n equals 1 is true, then n equals 2 is also true, since n equals 1 is true. Because you have like this plus 1. But also since like n equals 2 is true, then n equals 3 is also true, since 2 is true. Okay? So like you can do it like a domino. Some will describe it as a domino. Of course, like there are some set theoretical mathematicians are going to attack me because like I'm teaching it this way. But like let me just keep it like this, okay? Intuitively, like it's like this. If you want to prove like for n, say like 1000 is true, so you look for from this step you look for like 999, and then from this step again you look for 998, and like so on and so forth until you reach 1, which is true. So the whole implication is true. Okay. So the proof is as follows. So we're going to prove like for n equals 1 is true. It's usually like written as a base case. Some will even write trivial, since like it's really easy. To show an identity, to show an equation, you're not going to do the following. So this is not correct, right? It's like very usually written. You say like here is 1, since like you are adding 1 squared. And here you're substituting 1, 2, and 3. Like 1 in each thing. So you have 1 times 2 times 3, and then you're over the 6, okay? And then they're equal, so you're writing this. I mean, if it's really that simple, that easy, like you would make a substitution and it's like true, it's still fine, but it's not recommended. Since like if you have many steps, you may get into something wrong. Okay. The safest way, or like the most efficient way to do it, is as follows. So the way that I recommend is as follows. You do LHS. So LHS stands for like left-hand side. Okay, it's nothing fancy. Left-hand side, so you calculate, right? It's like 1 squared, so it's 1. LHS, right-hand side, you have this, you substitute n equals 1. So if 1 times 2 times 3 over 6, which is 1. Then you say that it is the same as LHS, right? So the statement is true for n equals 1. Okay. So here is the base case. So inductive step. So assume the statement is true for like n equals k, where k is a positive integer, probably. Okay. So you have like 1 plus 4 plus 9 plus ... plus k squared equals this. So you get it for free. Okay. So this is the power of mathematical induction. Since like you get a very similar statement for free, you don't need to prove anything like that. You just need to like carry on from that step to the next step. Okay. So now to prove is the like n equals k plus 1 case, right? It means that like to prove 1 plus 4 plus 9 plus ... plus k plus 1 squared equals, you replace all k by k plus 1, k plus 1. So if k plus 1, k plus 2, and 2 times k plus 1 plus 1. So it's 2k plus 3 over 6. Okay, this is something you want to prove. Okay, so we start from LHS. You know, it's like 1 plus 4 plus 9 plus ... I will write down the k squared in this step. Why? The thing for like when we want to use mathematical induction, it means that this step is very useful, right? And indeed, it's very useful. Since like you can see like the left-hand side, it's exactly the same as here. So we can replace this by k plus 1, 2k plus 1 over 6. And you have like k plus 1 squared, which is extra. Okay, so here we use the inductive hypothesis. Now, how to continue? I mean, you can expand like all the things, but like one thing you can try is to factorize. You factorize k plus 1, then you have like k 2k plus 1 plus k plus 1. Okay. You expand So you have like a 6, 2k squared plus k plus 6k plus 6. So here is from here, and here is going to be in here. Okay? And then you probably you just place them together. 2k squared plus 7k plus 6. So I will pretend that I don't know how to factorize this, okay? I mean, the factorization is not that hard. But let's go to right-hand side. So right-hand side is as follows. Here is the right-hand side. I just copy from here. Now, the k plus 1 is factored out as above. So we have like only k plus 2 and 2k plus 3. What do you do next? You factorize, you expand. It should be 8. No, it's 7. Yeah, I'm right. Nice. So now it's like the same as LHS. And here ends the proof. So of course, I'm not going to be able to cover all kinds of proof in math. And in fact, like there are many very beautiful techniques which are not covered here. However, I hope that this gives you an overview of like how you should read all the proofs and how you should attempt your assignments and how you should consider what is like so-called rigorous mathematics from now on. So thank you very much for watching and see you.